other scenes. Will you be mentioning some of the semantic segmentation?
Yes, actually I'm going to talk, pretty much the whole talk is about semantic segmentation from 3D data to the 3D.
Welcome.
Alright, so thank you very much for a nice introduction. I'm a PhD student in Filters Group at the University of Oxford, and I'm going to talk about recognition and reconstruction of outdoor scenes from streaming data, mostly from passive cameras, or actually just from passive cameras in this talk. And you can think about this task. So we're given a video sequence, and we want to recognize what happens at each frame. And as I'm going to talk a lot about segmentation, actually, let me start with a simple question. Why do we actually even need something more detailed than simple bounding boxes, right? Because we use bounding boxes everywhere in computer vision. So imagine we capture an image, and we run our favorite object detector, whatever it is, whether it's deep learning, your favorite object detector. So we detect some cars, some pedestrians, also some traffic lights. And as you can see, it works great. But this is in some sense the only information that you get from bounding boxes. And you can start asking questions such as, where's the road? Where's the pavement? Is this inside city or is it at countryside? And similar questions. Obviously, we can use some other sensors. I'm certain our friends from NRG would explain us much better. And you can also use rich prior knowledge. But let's assume for a while in this talk that we would rely just on computer vision, because that's probably going to be the cheapest sensor that you can use. So let's try to exploit as much information from that we can get from images as much as possible. So we need a bit more detailed description of a scene. So let's say, given a video, we want to assign to every single pixel either a class label or better probability distribution over potential labels. And this is so we actually want to recognize also stuff classes such as road, pavement, building, or trees. We want to recognize also moving objects such as cars and pedestrians, and we want to be able to reason about directions. So this is quite standard computer vision problem with very large body of literature. These are just few. We also have the standard data sets. These data sets consist of thousands and, well, these days, better to say millions of images, but these images are mostly static. And the funny thing is that actually most of our algorithms are developed with these data sets. So we develop our algorithms with static images, with the hope that on dynamic data or on videos, it will work better as the scores or the performance improves on these static images or on static data. Hopefully this will change with the new Oxford data set. That's definitely going to be useful for these types of algorithms. So I can ask a question, why do I want to talk actually about video data, about streaming data? Why is it different from static images if we use it everywhere? And why it's not enough just to take our standard algorithms, whatever we have, and take our videos, separate them into the frames, and apply our standard algorithms. That would be the simplest thing that we could do, right? So, just to motivate this work, I will show you this video. And this is actually exactly video sequence separated into independent frames, and each frame is analyzed independently by inference machine. And as you can see, it quickly results in flickering predictions, in temporal inconsistency, and this is definitely suboptimal for robotics applications if there appears objects just in front of car, disappears, and so on. By the way, this was the state-of-the-art performance 3 years ago, and even now, even with deep learning methods, you can observe similar issues. All right. So why don't we go to the completely other extreme? So instead of processing every single frame independently, why don't we try to take all the data we have and separate them just in a batch mode? So we'll just collect all the data, complete sequence, and just process it in one shot. Well, I think there are at least 2 good reasons why we cannot do that. So in robotics, or autonomous driving and applications like these, we need output on the fly. We cannot just capture a sequence, process it, and then do some decision. We need to get the output on the fly as the robot's moving. But even if we could do that, we probably wouldn't be able to fit all our data into the memory, because data these days, we have so much of data that we wouldn't be able to put it into memory and process it. So in some sense, we need to rely on some sort of mini batches that we can process, and we need to link them in some way, in some clever way. So temporal consistency is one issue, but there's actually much more. It shouldn't be just about compensating motion, but in fact we should actually do, our algorithms should actually benefit from motion. So typically you can assume that dealing with occlusions should be much easier from multiple views than just from a single image. You can assume that with videos you can use some temporal context or prior to whatever models at the test time. Action, activity recognition, this is another big field. And all these things that I will show today, they actually go beyond computer vision for cars. There are many more applications where we can use exactly the same tools or just slightly modified algorithms. Right, so in short, I'd like to see algorithms that are causal or online. That means that they do not need any information from future frames. That are efficient or work in near real time, because otherwise we cannot use it with real robots. Algorithms should also exploit extra information present in streaming data. They should handle pretty much any scale environment. We cannot say that processing, I don't know, this desk sequence is enough. We really need to handle any scale environments. And ideally, our algorithms should produce soft predictions. We ideally want to get probabilities. We want to have some notion of uncertainty, because computer vision is typically just the first step of the whole, in the whole system. So we don't want to do the hard assignments too early. Alright, and as I said in this talk, I will just show a very high-level overview of some algorithms that we've been developing in our group. And it will be mostly about passive cameras, and since it's going to be quite high level, so feel free to stop me whenever you want and ask me questions whenever anything's unclear or you want to know more details. So in the very first part, I will show a very simple smoothing algorithm that we published with my colleagues from CMU at least 3 years ago, I think. And you can figure out this problem. So we're given frames in t-1 and t. And we also have per pixel probabilities. So every single pixel is represented by a vector of probability. So we have probability over class 3, sidewalk, car, and so forth. And the goal is to make the predictions between t-1 and t consistent. And perhaps the natural thing might be to take some off-the-shelf optical flow and try to combine these predictions with dense optical flow. Because in theory it should provide you dense per pixel correspondences. However, getting dense per pixel correspondences is quite a difficult problem. So if you want to use dense optical flow as one-to-one mapping, it's probably not going to work well. But you can use dense optical flow as a coarse initialization. So instead of doing mapping from pixels to pixels, you can do mapping from pixels to neighborhoods. So in this case, we would like to use a neighborhood around a potential correspondence to smooth our current predictions in the current frame. There's just one little problem, and that's the fact that actually in this neighborhood we have pixels that correspond to the true class and also pixels that correspond to incorrect class. So we need to somehow weight them, otherwise we would oversmooth. So the most natural thing might be just to take simple pixel similarity, but if you use Euclidean distance, you quickly find out that actually it doesn't discriminate enough. So we took these reference points, and this actually visualizes the difference in the feature space. As you can see, it's so similar everywhere, so it won't help us much. So instead of this, we can actually learn a similarity metric in the max margin framework, such that we say that we want a distance between pixels corresponding to the same semantic class to be smaller than the distance between pixels corresponding to different semantic classes by some margin. And this can be actually formulated as quite simple convex optimization program, and if you collect a data set of such samples and solve it, you would learn a similarity metric that look, for example, like this. So this was learned over some simple features such as local binary patterns, gradients, etc. And in order to make it efficient, we actually use only the diagonal matrix, so that can be efficient at the test time. And when you actually use this length metric, you get output that looks like this one. So it's not globally optimal, but it discriminates much better, and that's what we're after. And when we put all these pieces together, you would get output that looks like this. It's not perfect, but you can see that actually the output is much more temporally consistent. And we actually try to use it with deep learning, with boosting, with inference machines, and with all these methods we observe quite similar behavior. Alright, I have also some numbers. So first we evaluated just overall pixel accuracy. And as you can see, we improved by 2 points or something like that. But it's probably more interesting to do a relative comparison. So we take only pixels where the base algorithm and the smoother differ. Because if the base algorithm is incorrect all the time, there's nothing what we can do. And the other way around, if the base algorithm is correct all the time, we cannot change anything. So we just compare those areas where the two differs. And as you can see, it produces quite large difference. Alright, so what's good and what's bad about this? So this enforces temporal consistency quite efficiently. You can use your favorite scene parsing output, so whether you use deep learning, CRF, inference machine, boosting, whatever you want, everything's fine. You can use your favorite optical flow method, any will work reasonably well, and it's very easy to implement. But on the other hand, it cannot fix major errors from the scene parser. It can oversmooth small objects. There are no structural constraints, there's no concept of objects. And in fact, there's even no concept of geometry. So, in some sense, just try to compensate motion, but we do not benefit at all. And that's exactly what we will try to fix right now by introducing 3D geometry or structure in order to improve the segmentation and also the temporal consistency. And the idea is that if we maintain our marginals on the 3D voxels, then actually it's much easier to get more accurate predictions, also more temporally consistent, because it's much easier to solve the correspondence problem for rigid scenes, and moreover we often just can actually just back project the data back to the parent view. So reconstruction and segmentation of point clouds is a very popular topic, but despite the large body of literature, most of these approaches suffer from some limitations. I don't want to go into the details, but typically they either assume indoor scenes or active sensors, or they work only in very small environments, or they first need to pre-capture these point clouds and then they can segment and so on. So we propose pretty much the first end-to-end system for dense, large-scale semantic 3D reconstruction for our scenes that worked from passive cameras in near real-time rates. And it has few nice properties. So first of all, it's an incremental algorithm. So you're getting the output as the robot's moving. You're incrementally reconstructing and segmenting the scene, and you're getting the output as the robot's moving. We use sparse data structures, so we're able to reconstruct almost any scale environments or large-scale environments. The semantic segmentation produces those soft predictions that I said that are useful. And we also handle moving objects more efficiently than the prior art. So how do we do that? So as an input, we use calibrated stereo camera. So we need to estimate both dense depth and also the camera poses through visual imagery. And then actually we can use fusion very similar to Kinect fusion, or actually the modification by Matthias Nisner that allocates only sparse points close to the actual surface. Because if we allocated the whole 3D volume, then actually most of the space would be unused, and that's wasting of memory. And this fusion actually quite efficiently streams the data between GPU and CPU, so that's another way how we can deal with memory, and this actually allows you to do the on-the-fly dense 3D reconstruction in large environments. So in the standard fusion, each voxel is actually represented as truncated sound system function, and it's updated as simple running average. But if you have some moving objects, you would start getting these ghost artifacts. So what we do is that we make this weight dependent on our semantic label, so that we can speed up the process of fusing the data in areas where we expect moving objects. So these are typically labeled as cars or pedestrians, And in these areas we can fuse this data more efficiently, and we can get rid of these artifacts. The last part of this pipeline is the actual semantic segmentation. So for this one, we use the standard features such as LBP or HOC. For data tram, we use the random forest classifier because it's very efficient. And then we use densely collected volumetric CRF, which is defined on top of our 3D model. And we use this to enforce the structural constraints between the neighboring voxels in a click. And because we need algorithm that will work in real time, we also need very efficient inference. So that's why we use mean field inference, because it is quite easily parallelizable on GPU and very fast. Right. How many of you want to ask me why didn't we use deep learning? Because it's 2016. So the only reason is that we didn't have CRF-SRM at the time when we did this work. But in fact, it's quite straightforward, and I will show it to you right now. So this is the standard pipeline that we used. And as the first thing, you can replace the handcrafted features and the random forest by a complement. In this case, we can use, for example, rich feature hierarchies by link. And we will put CRF on top of that. This is nice, but it doesn't allow you to do end-to-end learning of the whole model, which is quite useful for fine-tuning. So as the next thing, we can actually take this CRF, this mean field inference, and we can unroll it with RNN. And this is exactly what CRF-SRM paper does. And then actually you can do the fine-tuning over the whole model in an end-to-end manner, which is quite useful. And this was actually published by my colleagues at ICCV 15. Alright, now let's get back to the original pipeline, no deep learning anymore. So the top row shows the actual reconstruction as seen from the moving platform. So this is not the fly through the pre-reconstructed model. This is the output that you will see as the robot is moving. And the bottom row actually shows the segmented scene. And as you can see, that issue with temporal consistency in some sense disappears. We also have some numbers. Yes, we do improve, otherwise we wouldn't get a paper, but I think it's more interesting to show you the final fly-through through the reconstructed model, and this is how it looks like actually. So now let me make a very short detour. So today we've been talking about computer vision for autonomous cars, for all these things. But very similar technology can be used also for other applications. And I will now very briefly show you one such application we are very much interested in our group. So unfortunately there are more than 285 million people in the world living with sight loss. And this has a significant impact on their daily lives. But it turns out that more than 85% of them have some residual vision. So recently there has been an interest in developing augmented reality glasses. And these glasses should actually help them to provide more information about their environment. So this is work of our colleague Steve Hicks from the neuroscience department. Unfortunately, there's no sound, so you cannot hear it. But that guy actually he's just describing what he's able to see with these glasses. And as you can see, this is pretty simple thing. These are just simple edge detection and some regions filled by inverse depth. And this is pretty much the state of the art of the assistive technology for partially sighted. And as you can see, it helps quite a lot. But now imagine that we could extend these simple 2D renderings into full 3D models that would be segmented into semantically meaningful regions. And that's what we're trying to do in our group actually. But, and yeah, we could use the previous pipeline, but there are two small issues. The first one is that the users want to segment not just objects that we pre-train on some data set, such as, I don't know, we would be able to recognize chairs or cups, marks, and stuff like that. but they want to recognize their favorite cut, their favorite mark, and their personal things. So we need to put a user into the loop to allow to train this model on the fly. And second thing is also reconstruction, dense reconstruction from passive cameras is quite a difficult task. So we want to allow to clean up the segmentation somehow. So in this system, we use a pair of calibrated color infrared cameras and a standard laser pointer. These cameras are attached to see-through glasses for augmented reality, and we have laptops in our backpacks. And in our scenario, we actually assume that we have a visually impaired user and his guide. And in the first stage, the guide actually helps to the user to label the scene, label the environment, train the classifiers. And in the second stage, the user is actually navigated by our glasses and can walk on his own. So this is how it looks like. So now actually the guide shows a new class to the algorithm. Now that algorithm actually propagates this class into visually similar areas and learns classifiers in the background thread. And the final output that is shown to the user in the second stage looks like this. So there's quite clear pavement, road, trees, stuff like that. Alright, I've shown you some projects we've been doing, but in all of them something was missing. And what is it? So we haven't talked much about moving objects yet. And the thing is that if you want to reason about actions and about trajectories and these things, we need to track them in some sense to maintain the instances over time. So let me start with a paper called Struct, which was developed 5 or 6 years ago in our lab by Sam Hare. And this is an example of the tracking by detection paradigm. But in contrast to standard tracking by detection pipeline, it doesn't use this part where actually the problem is formulated as a classifier and we need to generate some samples and label these data. It's quite unclear how to do that. So this part is completely removed. And instead of this track is actually formulated in the structure prediction framework. And this directly allows you to optimize for the respective transformation, which is what we're after. We don't care about classification, we do care about the transformations. In fact, it extends structure output SVM by so-called budgeting mechanism. And that's, I will show it to you right now. That's the way how you can actually limit the number of support vectors to some fixed budget. And this is important because if you wouldn't do that, then actually you would be getting more and more and more support vectors and you wouldn't be able to use this algorithm for time-constrained applications, which we need in robotics. So this is quite principled approach and it's very competitive even on the recent benchmarks. But even if you use quite simple features, just when the feature vector is quite large and you use some kernels, it can be relatively slow. And this is not good because we typically need to track multiple objects. Just a single object is not enough. We usually need many more. We need to track many cars, many pedestrians, and so on. So an alternative approach is offered by so-called kernelized correlation filters. So typically in tracking by detection, we have some positive samples and negative samples. And these samples are actually somehow sampled sparsely around the object. So we typically put a student in the loop, and the student needs to figure out what would be the good trade-off for the sampling pattern, because we want to get many samples to get good performance, but on the other hand, we cannot have too many because it needs to be fast and so on and so on. But if you look at these samples, they are quite redundant and very, very similar. And this is actually something that is exploited in these kernelized correlation filters. So we can take the base sample and we can form a circular matrix. And then we can use the rich regression to learn the template. And this can be done very efficiently in the Fourier domain, and it leads to extremely fast test times. And another nice thing about this is that it completely removes this need for sparse sampling because everything is evaluated densely during the train time and during the test time. So the correlation filter pipeline looks like this. We start with an image and a bounding box, and we have some template. we compute a correlation score, we find the maximum response, and that in some sense defines the displacement. So in the next step, we actually move our bounding box, and we update the filter. And that's actually one iteration over one frame, and then we actually keep moving to the next frames. This works pretty well, but it assumes that our objects are very well represented by templates, which in other words says that objects do not undergo any out-of-plane rotation, non-rigid deformation, nothing like that. But this is quite common in outdoor scenes. So in order to fix this, we actually propose to use a second regressor that is trained on histogram scores. And the nice thing about histogram scores is that they are actually they are invariant to spatial permutations. So if there is some non-rigid deformation, the score would be very, very similar. And this can be again trained very efficiently and also evaluated through integral images. And I know this is really, really simple change, but despite the simplicity, it leads to really, really great performance. So it completely outperforms these more advanced trackers such as TLD or Struck. And in fact, it's scored as the top tracker on VOT14 benchmark, fourth on VOT15, second on CVPR13. But to be honest, this is even not the most important thing, whether we are better off by 1% or worse. That's not that big deal. But what really matters is that in the top 5, this is the fastest tracker by a large margin. So our tracker runs at 80 frames per second, while these competitors run typically in less than 5 frames per second. So you can actually track many more objects with this algorithm than what you can do with other methods. And we just released the source code because it has been accepted to CVPR16, so if you're looking for some fast and simple tracker, download it, use it, you'll be very, very happy. Alright, I talk quite a lot about segmentation throughout the whole talk, and we're obviously trying to extend these simple bounding boxes into segmentations even for moving non-rigid objects. But to be honest, it's quite unclear whether this is even needed for autonomous driving and these applications. Perhaps it's an overkill. But I'll leave this as an open question because it might be useful for some other tasks in robotics, such as very accurate manipulation and stuff like that. So just to summarize it, so segmentation definitely provides more information about the environment than just simple bounding boxes. Streaming data should be treated in a specific way because otherwise you can get some artifacts that you do not want to have in your output. 3D geometry helps quite a lot, and it is in fact able to solve the static part of the environment. But the moving objects should be treated separately, or they should be actually tracked. And despite the segmentation is quite a nice idea, there's one little tiny issue that I haven't mentioned, and that's the fact that it produces per pixel maps. And there's actually no concept of objects, so you have no idea how many objects are in the scene. You would just get actually a per pixel map. And if you want to solve it, you probably need to go into something like joint segmentation detection or joint segmentation classification. So I would just like to thank all my collaborators, and these are the main references, and I thank you for attention, and I will take your questions.
Thanks for the talk. I really agree with your message on, I guess, going forward with video data and the streaming setting. But one, I might have misunderstood this, but one of the, just talking about your semantic reconstruction system, it seems like you've got this, on one hand you've got this stereo sort of reconstruction system to create a 3D representation. On the other hand, you've got this semantic segmentation system, and it looks like you're applying this segmentation system to paint the 3D model within semantic classes. Do you think there's maybe an obvious next step, or I don't know if this is included in the work, of actually bringing them, not combining them at this stage, but at a lower stage combining them and perhaps using some semantic knowledge in this reconstruction process to guide that?
Yes, I think there's a way how to do that. In fact, there are some papers that try to do joint reconstruction and segmentation, I think from ETH, from Mark Welfay's group. And you can see that there are also many papers that try to combine, for example, passive cameras and LiDARs, but not actually in the final stage when they try to combine the actual classifications, but first they try to densify, for example, the depth maps, in fact we did it in this paper. And in the same way you can actually try to start actually including the semantic information into it at the very first stage, even before you actually start fusing the data into the model.
Sure. And the other way with the 3D reconstruction.
Yes. So the 3D reconstruction already helps actually even in this work, because we actually use our pairwise potentials are actually based on this 3D information, so it already actually helps.
I have a question from a practical point of view. So let's say this work is really good and I would like to actually apply it on the car and steer a car with it. How good it is with respect to changing lighting conditions, any sort of like real world scenarios, you know? How the data is work?
Yeah, that's a great question. So we mostly work actually with the Kitty dataset, because that was probably the only one that was available with automated cameras, semantic labels, and all these things that we wanted to use. Hopefully now it will change with the new data set by these Oxford guys. So that's an open question how well it works. But I can say that the demo that my colleagues released for the CRMS RNN, which is actually modeled semantic segmentation, they released the online demo, and people started uploading images from that the model actually never seen before. And I was quite surprised how well it works. Obviously, this says nothing about changing lightning and weather and these things, which are all great programs. But I think there is at least some hope. Yes.
Thank you very much. The work on the joint real-time semantics is really impressive. There's a certain trade-off, I guess, if you, for this HD streaming paradigm, if you increase your frame rate, you actually have to only look at a couple of new appearing pixels.
Yep.
Well, if you, at the same time, you probably don't need like semantic labels at 30 frames per second.
Yes.
5 or 10. Did you look at that?
No, we haven't looked into this, but I think there's a paper from Bastien Leib's group from ICRA 14, and they actually looked a bit into this scheduling, where actually and they try to actually examine whether you really need semantic segmentation at each frame, or whether you can do it each 5th frame or 10th frame and so on, to actually maintain the budget in a bit better way. We haven't looked into it, but it's definitely a great direction to go. Because, as you said, the higher the frame rate, the simpler things are in terms of tracking and reconstructing these things. So